This is the story of the one. As a maintenance supervisor at a manufacturing facility, he knows keeping the line up and running is a top priority. That's why he chooses Grainger. Because when a drive belt gets damaged, Grainger makes it easy to find the exact specs for the replacement product he needs. And next day delivery helps ensure he'll have everything in place and running like clockwork. Call 1-800-GRAINGER, click Grainger.com, or just stop by. Grainger, for the ones who get it done.
Bugs crashing your pack's party? Whether they've got paws or sneakers, your pack deserves a home that's protected from pests. That's where Wondercide comes in. Plant-powered protection made with steam-distilled natural essential oils that actually work. It kills and repels fleas, ticks, mosquitoes, and ants without questionable ingredients or overpowering smells. Safe to use around kids and pets when used as directed, lab-proven to work fast, and proudly made in the USA. We offer sprays for pets, people, homes, and yards. Plus, spot-on treatments, collars, and even shampoos. Whatever your pack needs, we've got it covered. Founded by a pet parent looking for a better way to protect her dog Luna, Wondercide's now protected over 21 million lives and counting. You might have even seen us on Shark Tank. Go to Wondercide.com and use code WONDER20 for 20% off your first order. That's WONDER20 at Wondercide.com. Wondercide. Protect your pack with plant-powered Wondercide today.
Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing bedtime astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
Imagine a burst of energy, so mind-bogglingly powerful. It could actually outshine our sun's total output for 10,000 years.
Wow.
And all of that compressed into, well, just a mere millisecond.
Just a millisecond.
Yeah, it's a flash quicker than you can blink, really. Yet it unleashes this almost incomprehensible amount of cosmic force. What in the universe could possibly cause such an incredible fleeting event?
It does sound like science fiction.
Doesn't it? But these phenomena, they're very real. They're some of the universe's most enigmatic signals. And honestly, they've been baffling astronomers for years now.
You've really hit on one of the biggest cosmic puzzles out there. And it's a perfect way to open this deep dive. For well over a decade now, the scientific community has indeed been wrestling with the mystery of fast radio bursts, or, FRBs as we call them.
Right, FRBs.
These are rapid, intensely powerful, and maybe most frustratingly for researchers, incredibly unpredictable flashes of radio waves.
Yeah.
They seem to appear out of absolutely nowhere and then vanish just as quickly. Gone. And their transient nature, combined with that immense energy you mentioned, has made them incredibly difficult to pinpoint, let alone explain. It's like trying to catch lightning in a bottle.
Yeah.
But the lightning is happening millions or sometimes even billions of light years away.
And that's exactly the cosmic detective story we're going to dive into today. Because just recently, astronomers made what many are calling a truly groundbreaking discovery.
That's right.
They detected one of the brightest fast radio bursts ever observed. Initially, it was designated FRB 22503116A.
Catchy name.
Not exactly rolling off the tongue, no. But very quickly, and I think quite fittingly, it got nicknamed RB Float.
RB Float, I like it.
It stands for Radio Brightest Flash of All Time. And the excitement among researchers about this particular event, it's absolutely palpable.
Oh, definitely.
And for incredibly good reason. This might just be the most significant clue we've had yet in the hunt for what powers these cosmic bombshells.
Yeah, our mission then in this deep dive is really to pull back the curtain on this profound discovery. We'll explore what fast radio bursts are, at their core, delving into the physics of these really extreme events.
Okay.
Then we'll unpack what RB Float specifically tells us about these mysterious cosmic explosions. And perhaps most importantly, we'll try to illuminate the revolutionary techniques astronomers are now using to finally get a clear view behind that cosmic curtain.
Techniques that seem to be really paying off now.
They really are. We're talking about a significant leap forward in understanding phenomena that have for a long time just defied easy explanation.
And all of this fascinating, really cutting-edge information, the foundation of our deep dive today, it comes to us from a captivating article published just recently on Sci News. It details how astronomers discover one of brightest fast radio bursts ever detected, and it hit the digital presses just a short while ago, August 22, 2025. So, very fresh science.
Very fresh. And what's truly compelling about this particular discovery and why it forms such a rich foundation for our deep dive is how it masterfully pulls together these cutting-edge observations from a whole suite of advanced instruments.
Right. It's not just one telescope.
Exactly. We're not just relying on one type of data here. We're talking about the CHIME Outriggers array that's specifically designed for detecting these bursts with unprecedented accuracy.
Okay.
And that's working in tandem with the unparalleled capabilities of the James Webb Space Telescope.
Webb, yeah. Powerful combination.
It really is. Together, these tools are giving us an extraordinary and, frankly, an entirely new window into something that has long been one of the universe's most tantalizing riddles.
Yes. Okay, let's unpack this cosmic enigma then. Let's start with the fundamentals. What exactly are fast radio bursts?
Right.
At their most basic, FRBs are, well, precisely what their name implies.
Yeah.
Incredibly brief, intensely brilliant explosions of radio waves. But the key here, as you touched on, is their origin. They're overwhelmingly of extragalactic origin.
That's the crucial part, extragalactic.
Meaning they're not some local phenomenon happening, within our own Milky Way galaxy. They're coming from unimaginably far beyond, across immense, just mind-bending cosmic distances.
And what's truly astonishing about them is that brief and brilliant aspect you mentioned. When we say brief, we mean truly, truly fleeting.
Like how brief are we talking?
These events typically last for mere milliseconds, so to give you a real sense of that, it's a duration shorter than the average human eye blink.
Wow.
Which is about, 100 to 400 milliseconds, and much faster than that. Yet, despite their extraordinarily short duration, they emit an immense, almost unfathomable amount of energy.
Okay, quantify immense here.
Well, the source material highlights that a single FRB in that 1 millisecond flash can release as much energy as our sun produces over 10,000 years.
10,000 years.
Yeah.
Of the sun's output.
In a millisecond.
That's just, I can't even picture that.
It's staggering. Imagine capturing 10 millennia of solar output, all that light, all that heat, and compressing it into a single instantaneous flash. That's the sheer scale of power we're dealing with.
It really challenges our understanding of how such an event could even be physically possible, doesn't it?
Absolutely.
Yeah.
How do you generate that much energy so quickly?
That's a truly jaw-dropping amount of energy for such a short time. And to really grasp the scale and the brevity, maybe a picture like this. Imagine a camera flash.
Okay.
But instead of just lighting up a dark room for a fraction of a second, this flash somehow manages to light up, an entire continent. Brighter than anything you've ever conceived, only to vanish into the darkness just as quickly. The sheer power involved is mind-boggling, and that brevity makes them incredibly elusive.
Exactly.
But the central puzzle, as you said, isn't just how much energy is released, but what actually causes it.
Yeah.
That's been the enduring fundamental question driving this whole field of research, hasn't it?
Precisely. And this brings us to the fascinating history of their discovery, which itself reads a bit like a scientific detective story.
Oh. How so?
Well, the very first FRB was technically discovered in 2007 by a team led by Duncan Lorimer.
Okay, 2007.
But the actual observation of that signal happened some 6 years earlier, back in 2001.
6 years earlier, so it was just sitting in the data?
Exactly. It was hidden, patiently waiting, within archival data specifically, from a pulsar survey they were doing of the Magellanic Clouds.
So they weren't even looking for FRBs then?
Not at all. Nobody knew they existed. It wasn't until astronomers, figured out what unique signature to look for, this kind of dispersed signal, that this Lorimer burst, as it's called, was finally pulled out from the noise.
Wow. That timeline really highlights how challenging FRBs must have been initially. Imagine finding a signal from 2001, 6 years after it happened, buried in data nobody understood.
It truly was a needle in a haystack problem.
I bet. The sheer volume of radio data collected by observatories must be immense.
Oh, it is. Petabytes.
And before scientists knew what a fast radio burst even was, these fleeting signals must have been incredibly difficult to distinguish from just, everyday radio interference right here on Earth. Or maybe just dismissed as random noise.
That's exactly what happened. The data was there, but the signature was so unusual, so brief, that it just didn't immediately stand out. It took a specific search, looking for that specific kind of dispersed signal.
It really speaks volumes about the incredible patience, the painstaking work, and maybe just the sheer ingenuity of the astronomers who finally recognized that something unusual was lurking in those archives.
Absolutely. And the key to identifying them, as you mentioned, is this unique characteristic known as a dispersion sweep.
Dispersion sweep. Okay, what's that?
Right. So it's not just a quirky signature, it's a fundamental physical phenomenon. It acts like a cosmic fingerprint. Radio waves from deep space, as they journey across millions or billions of light years,
Right.
they travel through this diffuse plasma, basically, ionized gas that fills the interstellar and intergalactic medium. It's not empty space out there.
Okay, there's stuff between galaxies.
There is. And crucially, lower frequencies of radio waves get slowed down more by this plasma than higher frequencies do.
Ah, okay. Like light through a prism, but for radio waves in time.
That's a great analogy. So when an FRB hits our telescope, we detect the higher frequency waves arriving first, followed very rapidly by the lower frequency ones. It creates this characteristic downward sweep in arrival time across the radio spectrum.
So it smears the signal out slightly in time, depending on frequency.
Precisely. It's like listening to a bass note arrive fractionally after a treble note from a very, very distant orchestra. And that precise delay, that dispersion measure, tells us two critical things.
Okay, what are they?
First, it tells us the signal is almost certainly from deep space because Earth-based interference wouldn't travel through enough plasma to get dispersed like that.
Right, eliminates local noise.
Exactly. And second, it gives us a vital clue about the distance the signal has traveled. The more dispersion, generally, the farther away it is because it's passed through more intervening cosmic plasma.
So it's a distance indicator, too.
It is, albeit an approximate one. Without that Peltier signature, these phenomena truly would be indistinguishable from, microwave ovens down the hall or just random static.
Right, which is probably why they were missed for so long.
Absolutely. For years, these bursts were just fleeting ghosts in the cosmic machine. Tantalizing glimpses of extreme physics, often only noticed long after the fact in old data. But now, with dedicated instruments like CHIME and advanced computational techniques specifically designed to detect this signature in real time.
We're catching them live.
We are. We're not just finding them anymore. We're zeroing in on them with incredible precision, almost as they happen.
And as you can imagine, with such an extraordinary and mysterious phenomenon, something so powerful, so fleeting, coming from the depths of space, there've got to be plenty of theories and speculations about their origin.
Oh, absolutely. The floodgates were open for a while there.
Because the exact physical phenomenon causing FRBs, it remains largely unknown, right? Which naturally opens the door to a wide range of scientific hypotheses.
It does. And our source material outlines two main categories of theories that astronomers are actively considering, or at least have considered seriously.
Okay, what are the main contenders?
Well, on one hand, you have what are now the most widely accepted scientific theories. These center around highly magnetized neutron stars, which we often refer to as magnetars.
Magnetars. Okay, I've heard of those. Remind me what they are.
They are truly exotic objects. They're incredibly dense, rapidly spinning remnants left over from massive stars after they explode as supernovae.
So dead stars, essentially.
Very energetic dead stars. They possess magnetic fields that are quadrillions of times stronger than Earth's.
Oh, drillions. That's hard to grasp.
They're the most powerful magnets known in the universe. And one leading theory suggests these magnetars could be blasted by streams of gas near a supermassive black hole.
Whoa, okay, so a magnetar near a giant black hole? That sounds like a recipe for fireworks.
Exactly. Imagine the extreme gravitational and magnetic forces interacting in that environment. It's like a cosmic pressure cooker, where immense energy could be suddenly unleashed in a powerful, focused beam, maybe as material from the black hole's accretion disk interacts violently with the magnetar's field.
And the sheer energy output from something like that.
It fits the bill for an FRB. The energetics line up pretty well.
Okay, so that's the sort of natural astrophysical catastrophe theory. What's the other category?
Well, then on the other side, you have a much more speculative, but still sometimes considered explanation. And that's the idea that FRBs could be signatures of technology developed by an advanced civilization.
The ET hypothesis.
Essentially, yes. Now look, while this idea often gets relegated, quite rightly, to the realm of science fiction,
Usually does.
the sheer power, the very distinct, highly localized nature, and especially the fact that some early FRBs were found to repeat, sometimes even in a complex pattern.
Right, the repeating FRBs were particularly puzzling.
They were. And those properties have, at times, kept this advanced civilization theory alive in a small segment of the scientific community. It really just underscores how truly unknown the nature of these events was for a long time.
But we should be clear, right? The scientific community needs extraordinary evidence for extraordinary claims like that.
Absolutely. We must emphasize that the bar for evidence regarding extraterrestrial intelligence is extremely high, as it should be. And to date, there is no credible evidence supporting the advanced civilization hypothesis for FRBs.
Okay.
But the fact that such a possibility was even entertained, even briefly, by serious scientists, highlights just how profoundly perplexing these signals were. It forced astronomers to consider the broadest possible spectrum of explanations, from known physics pushed to extremes, all the way to, well, something else entirely.
It's a stark contrast, isn't it? On one side, you've got the raw, unbridled power of natural cosmic catastrophe, fundamental physics playing out in the most extreme environments imaginable, a universe of immense energies and truly bizarre objects. And on the other side, the almost equally awe-inspiring, if currently completely unsubstantiated, idea of intelligent design. A deliberate signal from some civilization far beyond our own, using technology we can't fathom to broadcast across galaxies.
It really does highlight just how perplexing FRBs are. They simultaneously push the boundaries of known astrophysics and, challenge our preconceptions. But our latest discovery, this RB float.
Yes, RB float.
It might just be the crucial piece of evidence we've been waiting for. It's providing tangible data that could finally tip the scales and bring us closer to a definitive, scientifically grounded answer.
Speaking of RB float, let's turn our attention right there to this beacon from the barred spiral galaxy. The event, formerly FRB 22503168, affectionately RB float,
much better,
was definitively detected on March 16, 2025. Now, what makes this specific burst so incredibly special? Why is it garnering so much attention?
It's the brightness. It has been definitively labeled as one of the brightest fast radio bursts ever detected by humanity, a truly monumental observation in terms of signal strength.
And why is brightness so important here, especially for something this elusive?
Well, in astronomy, it's almost always true. The brighter an object, the easier it is for our telescopes to gather meaningful data from it.
And more photons, basically.
Exactly, more signal. A brighter signal often translates to a much higher signal-to-noise ratio. That means you get more detail, clearer observations, and a much stronger ability to overcome all the cosmic noise and interference that typically plague these kinds of detections.
Especially compared to fainter bursts that are barely above the background hiss.
Precisely. RB float's exceptional luminosity gave astronomers an unprecedented observational advantage. It was almost like turning a dimmer switch all the way up on a previously faint, flickering light. Suddenly, it's a brilliant, unmistakable beacon.
That clarity, that brightness, must have allowed for follow-up observations that just wouldn't have been possible for dimmer events.
Absolutely critical.
That's a fantastic analogy. Trying to study a faint flicker across a dark room versus having a powerful spotlight shining right on the object you want to examine.
RBF float is the spotlight.
It provided a much clearer, much more robust target for those crucial follow-up observations, which, for such transient, millisecond-long events, is absolutely make or break.
It really is.
Without that initial brilliant flash, the astronomers wouldn't have had the precise location needed to quickly train other, more sensitive telescopes on its origin point.
You need that accurate address fast.
And where did this cosmic spotlight shine from? A galaxy with a name that, well, maybe not as poetic as Andromeda, but it rolls off the tongue as a scientific designation. NGC 4141.
NGC 4141 it is. RB float originated in the outer regions of this galaxy, NGC 4141, which is classified as a barred spiral galaxy.
A barred spiral, like our own Milky Way, potentially.
Very likely, yes. Our Milky Way is thought to be a barred spiral. It's a common type. This particular galaxy, NGC 4141, is located approximately 130 million light-years away from us.
130 million light-years.
And it's nestled within the familiar constellation of Ursa Major, which, for many of us in the Northern Hemisphere, is recognizable as the Great Bear, or, the Big Dipper.
Okay, so relatively nearby in cosmic terms, but still incredibly far. What exactly is a barred spiral galaxy?
Right, so it's a type of spiral galaxy, but unlike a regular spiral, it has this prominent, elongated, bar-shaped structure made of stars and gas stretching across its center.
A bar through the middle.
Exactly, and the spiral arms typically extend outwards from the ends of this central bar. Our own Milky Way, as I said, is thought to have a bar. The presence of a bar can significantly influence how the galaxy evolves, things like star formation rates, how gas moves around.
Which could be relevant to where extreme events like FRBs might happen.
Potentially, yes. The dynamics are different in barred spirals.
And that distance, 130 million light years. It's just staggering when you stop and think about it.
It really is.
A light year, the distance light travels in a year, is already vast, nearly 6 trillion miles. So when we saw RB float in March 2025, those radio waves have been traveling for 130 million years.
Since the time of the dinosaurs?
Exactly. We're not seeing NGC 4141 as it is today, but as it was when dinosaurs roamed the Earth, when Pangea was just starting to break apart. It makes you wonder, doesn't it? What incredible cosmic events, what profound changes might happen in the universe during those 130 million years, while those radio waves were just steadily crossing the void to reach us.
It's an incredible journey through time and space captured in that single signal. Truly mind-bending.
Knowing its galactic home, NGC 4141, that's one thing, a remarkable feat in itself. But pinpointing the source within that galaxy, narrowing down its exact cosmic address, that sounds like serious cosmic detective work.
It is, akin to finding a specific house in a city that's 130 million light years away, yeah.
And that's where the CHIME Outriggers came in, right?
Yeah.
Providing that crucial next step.
That's precisely it. The detection and, more importantly, the precise localization of RB float was made possible by the CHIME Outriggers array.
That's the radio telescope network in Canada.
Correct, and this array was recently upgraded specifically to enhance its capabilities for FRB detections, particularly by enabling extremely precise positional accuracy.
And that precise positional accuracy isn't just a technical detail, is it? It's the game changer here.
Absolutely. For years, the major hurdle in FRB research wasn't just detecting them, but locating their origin with enough precision to actually study their host environment. Early FRBs, they were often localized only to a very broad region within a galaxy, or sometimes just pinned to the galaxy itself.
Leaving a huge area to search for the source.
Exactly. A vast cosmic haystack.
So how precise are the Outriggers now?
It truly is a game changer. Imagine trying to find a single spark in a city-sized blackout. The CHIME Outriggers upgrade is crucial because it now allows astronomers to narrow down the source not just to an entire galaxy, but, as Dr. Amanda Cook from McGill University put it so well, even to specific stellar environments.
Specific stellar environments?
Yeah.
Like star clusters or even near individual stars?
Potentially, yes. This level of precision is achieved through a technique called Very Long Baseline Interferometry, or VLBI.
VLBI.
It combines the signals from multiple widely separated radio telescopes, the Outriggers, working with the main CHIME telescope to effectively mimic a single giant telescope. The greater the separation between the telescopes, the finer the detail they can resolve.
So bigger baseline equals sharper vision.
Exactly. The Outriggers essentially extend CHIME's baseline across a large part of North America, allowing for localization down to arcsecond level precision.
Arcsecond. How precise is that?
It's equivalent to being able to see, say, a car on the moon from Earth.
Wow. Okay, that is precise.
It's an incredible leap. It means we can now start to identify potential individual stars or star clusters that might be the immediate progenitors of these bursts.
I love that quote you mentioned from Dr. Cook. It really brings home the excitement. With the CHIME Outriggers, we are finally catching these fleeting cosmic signals in the act, narrowing down their locations not only to individual galaxies, but even to specific stellar environments.
It captures it perfectly.
That's an incredible leap in observational capability. We're moving from these broad strokes to incredibly fine detail. And this precision, it wasn't just an achievement in itself, was it? It opened a crucial door.
It did. It allowed another even more powerful eye to turn towards RB float's origin, the James Webb Space Telescope.
The perfect synergy. Radio finds it, Webb zooms in.
Precisely. A testament to the power of combining different astronomical instruments.
And this leads directly to that rapid follow-up with Webb, which sounds like it was a feat of coordination as much as technology.
It absolutely was. A testament to both cutting-edge tech and exceptional human coordination across international teams. Following CHIME Outriggers' precise localization of RB float, Dr. Cook and her team wasted absolutely no time.
They had to move fast.
Extremely fast. They quickly utilized the NASA-SAXA James Webb Space Telescope, JWST, to search for an infrared signal from the exact same newly pinpointed location that CHIME had identified. The planning and execution of this rapid response were, frankly, formidable. You have to remember how sought-after observation time is on a flagship telescope like Webb.
I can only imagine. Getting time on Webb is notoriously difficult.
It is. So triggering it this quickly for a transient event is a major achievement.
And the speed, the coordination required.
Yeah.
It can't be overstated, can it? FRBs are by definition transient. They come and go in milliseconds.
Blink and you miss it.
So a swift follow-up observation, ideally within hours or days, is absolutely essential before any lingering electromagnetic signature, maybe an afterglow from the burst, fades completely.
You have to catch any residual heat or light.
And Webb's capabilities seem perfectly suited for this. Its powerful infrared eye is incredibly adept at studying distant cosmic phenomena. And crucially, infrared light can often see through the thick dust and gas that would obscure observations at visible wavelengths, right?
That's a key advantage. It allows astronomers to peer into potentially dense star-forming regions within NGC 4M41 with unprecedented clarity, regions where visible light might not penetrate.
So choosing infrared wasn't just about sensitivity, it was strategic.
Very strategic, vital even.
Dr. Peter Blanchard, an astronomer at Harvard and Smithsonian's Center for Astrophysics, he captured the unique nature of this moment perfectly, didn't he?
He did. He stated, this was a unique opportunity to quickly turn Webb's powerful infrared eye on the location of an FRB for the first time.
For the first time. That really highlights the unprecedented nature of this direct, rapid, multi-messenger follow-up, marrying the precise radio detection with deep infrared scrutiny.
It genuinely represents a new era in FRB research. We're moving beyond just statistical studies of large populations of FRBs to doing detailed case studies of individual bursts and their immediate environments.
It's like moving from hearing a distant explosion and maybe knowing the neighborhood to actually seeing the specific building it occurred in, and then immediately rushing in with an infrared camera to see what's glowing inside.
That's a perfect analogy.
And the reward. For all this swift action, all this cosmic detective work, did Webb find something?
Oh, it did! An exciting result that offers the clearest view yet into an FRB's potential home. Webb's infrared data didn't disappoint. It provided a crucial piece of the puzzle.
Don't leave us hanging. What did it see?
Okay. The telescope revealed a faint but distinct source of infrared light very, very close to where the radio burst occurred.
A faint infrared source, right at the location.
Exactly. This intriguing object was immediately dubbed NIR1. Stands for Near-Infrared Source 1.
NIR1, okay.
And the profound implications of this finding are immense, truly a monumental step. Dr. Blanchard's excitement was palpable when he shared, and we were rewarded with an exciting result. We see a faint source of infrared light very close to where the radio burst occurred. And even more significantly, he added something that really resonated across the astronomical community. This could be the first object linked to an FRB that anyone has found in another galaxy.
The first object potentially linked to an FRB source in another galaxy.
That's the claim. It represents a monumental, truly game-changing step forward in FRB research. It moves us from purely theoretical speculation and statistical analysis to having a concrete, tangible candidate for an FRB progenitor in another galaxy.
It shifts the conversation entirely from what could it be to what is this specific thing we're seeing right here?
Precisely that.
You can almost imagine the collective gasp, the flurry of emails and discussions in the astronomy community when this faint infrared signal was confirmed.
Oh, absolutely. A major buzz.
It truly means we're no longer just making educated guesses based on galactic properties. We have an actual spatially resolved target.
Yeah.
A specific location to investigate. It feels like a real plot twist in this cosmic mystery.
It really does.
So what is this mysterious NIR1? Does Webb's data immediately tell us what it is, or are there still a few strong contenders?
That's the crucial next question, isn't it? And the data, while incredibly insightful, still leaves us with a couple of compelling possibilities. It's not a slam dunk just yet.
Okay.
Based on Webb's infrared data, looking at its brightness, its color, NIR1, is most likely a red giant star.
A red giant.
Yeah.
Like our sun will become one day.
Exactly like that. A sun-like star nearing the end of its life cycle. It's exhausted the hydrogen fuel in its core, expanded dramatically to many times its original size, cooled down, becoming much redder and significantly more luminous than it was.
Okay, so an elderly expanded star, that's one possibility. What's the other?
The alternative is possibly a middle-aged massive star.
A massive star. How massive are you talking?
Much larger than our sun, often tens of times the mass. These are far more luminous, live much shorter, more dramatic lives, and typically end their lives in violent supernova explosions.
So two very different types of stars, both quite common celestial objects, though.
Relatively common, yes.
But here's the kicker, right? The twist in this scientific mystery. The source material explicitly states that these stars themselves are unlikely to directly produce FRBs.
That is the crucial point. Nail on the head.
So, if NIR1 is one of these stars, a red giant or a massive star, then it's not the direct culprit for the cosmic flash itself.
It's likely not the engine.
Which immediately shifts our focus. It implies there's something else interacting with NIR1, right? An unseen partner maybe that's actually triggering the burst.
Exactly. You've hit on the key implication there. If NIR1 is the visible star we see, but it's not intrinsically generating the FRB, then we need to look for a hidden actor. A partner in crime, so to speak.
Okay.
This leads us directly to a leading hypothesis. The companion hypothesis.
The companion hypothesis. Tell me more.
It suggests that NIR1, whether it's the red giant or the massive star, has an unseen companion orbiting it in a binary system.
An unseen partner. What kind of partner?
Well, the theory suggests this companion is likely an incredibly dense, compact object, something like a neutron star.
A neutron star. Back to those again.
Back to the usual suspects. This neutron star companion would be gravitationally pulling material away from the visible star, NIR1.
Siphoning off its atmosphere.
Essentially, yes, through a process known as mass transfer. And it's this intense process of mass transfer, perhaps leading to extreme conditions or sudden instabilities around the neutron star, that may have then triggered the fast radio burst.
Okay, this is where it gets really interesting. It connects the dots back to our earlier theories about magnetars and neutron stars.
It does indeed.
Because a neutron star companion would be incredibly dense, incredibly compact, basically a collapsed stellar core, and therefore likely way too faint to be seen directly by Webb, especially 130 million light years away.
Exactly. It would be hidden in the glare of NIR1 or just intrinsically too dim.
But the mass transfer mechanism itself sounds fascinating. One star literally stripping material from its neighbor due to gravity.
It happens all the time in binary systems.
And that process must create incredibly extreme conditions around the neutron star, right?
Oh, absolutely. You're talking about accretion disks of superheated gas swirling around the neutron star at incredible speeds, maybe close to the speed of light. You've got powerful magnetic fields getting twisted up, tangled, maybe snapping and reconnecting violently.
Magnetic reconnection.
Like
solar flares, but on a vastly more energetic scale.
Potentially, yes, and immense gravitational forces that can generate tidal stresses. It's precisely these kinds of extreme dynamic environments, the interface between the stolen gas and the compact neutron star, that could plausibly generate the sudden, powerful burst of energy we see as an FRB.
Maybe through one of those magnetic reconnection events, or perhaps some kind of instability in the accreting matter hitting the neutron star surface.
Those are the kinds of mechanisms being modeled, yes. This theory strongly ties back to the general highly magnetized neutron star idea for FRBs, but it places it specifically within the context of an interacting binary star system. It provides a concrete physical mechanism for activating the neutron star, making it burst.
It's a compelling narrative, a plausible, physically consistent way to generate that much energy so quickly. This binary system idea sounds strong.
It is certainly strong. It offers a neat package, but the researchers, being thorough scientists...
And put all their eggs in one basket?
Exactly. They explored all avenues. They broadened their search beyond just NIR1 itself, looking at the immediate neighborhood around it.
Okay, what did they find nearby?
They found that the FRB location isn't just near NIR1, it's also near a small cluster of young, massive stars.
A cluster of young stars. Interesting. How does that fit in?
Well, based on this additional observation, they proposed an alternative explanation.
Another suspect in the lineup.
Pretty much. The alternative is that a massive star within this cluster might have already lived out its short, violent life and collapsed to form a magnetar.
Ah, so an isolated magnetar this time, not in a binary.
Potentially, yes. This magnetar, a highly magnetic neutron star born from a recent supernova within that cluster, could then have produced the FRB directly, perhaps through processes internal to itself, like those sudden magnetic field rearrangements we talked about, sometimes called starquakes, on the neutron star's crust.
Starquakes? Cool concept.
It's in it. And again, just like the hypothetical neutron star companion in the binary scenario, this isolated magnetar would likely be much too faint for Webb to see directly at that distance.
So it's still consistent with the observations or lack thereof.
Exactly. This introduces the other main competing theory for FRB origins. An isolated magnetar, likely a young one. Massive stars, unlike our sun, have incredibly short lives, millions of years, not billions.
Live fast, die young.
Precisely. They burn through their nuclear fuel rapidly and end violently in those supernova explosions, leaving behind remnants like neutron stars. And if the conditions are just right, maybe rapid rotation, intense magnetic fields in the original star, these neutron stars can become magnetars.
The universe's supermagnets.
That's them. So this alternative hypothesis places the FRB in a region of recent, intense star formation, that young cluster where such massive stars are born, live fast, die young, and then potentially leave behind the very objects capable of generating FRBs.
Professor Ido Berger, also from Harvard and Smithsonian, he really underscored the significance of being able to see this environment, didn't he?
He did. He said, being able to isolate individual stars around an FRB is a huge gain over previous searches, and it begins to tell us what sort of stellar systems could produce these powerful bursts.
It really underlines the immense value of the granular detail Webb provides. It allows us to connect FRBs to specific stellar environments, not just vague galactic regions.
It's moving from demographics to individual case studies, a huge step.
So, okay, let's recap the suspects. We have two incredibly strong contenders for what caused RB float. Contender number one is a hidden neutron star stripping material from a visible companion star, NIR1, either a red giant or a massive star in a binary system.
Mass transfer scenario, right.
And contender number two is an isolated magnetar, probably young, residing within that nearby cluster of young, massive stars born from a recent supernova in that cluster.
The isolated magnetar scenario.
Both scenarios are incredibly intriguing. Both seem physically plausible, and both are consistent with Webb not directly seeing the engine itself.
That's the current state of play. Two very viable paths.
But being meticulous scientists, the team also did the important work of ruling out some other possibilities, didn't they? Which is just as vital in science.
Absolutely. Ruling out hypotheses is as crucial as identifying new ones. It narrows the field, strengthens the remaining theories by eliminating alternatives. The team carefully considered other explanations for the FRB that might have fit the broad description.
Like what, for example?
For instance, they look at the possibility that the FRB might have originated from an object within a really dense cluster of old stars, like a globular cluster.
Okay, different kind of environment.
Very different. Or maybe from an exceptionally massive superluminous giant star, perhaps one much, much brighter than NIR1 turned out to be.
Right.
However, these types of objects, if they were the source, would have been significantly brighter in Webb's infrared observations than the faint NIR1 they actually detected.
So NIR1's faintness was actually a key clue.
Exactly. Because NIR1 was so faint, these other brighter scenarios just didn't fit the data. They were inconsistent with what Webb saw, and so they were subsequently ruled out. That observational constraint is powerful.
That's a fantastic demonstration of Webb's power right there.
Yeah.
The faintness wasn't a limitation. It became a crucial piece of evidence that directly constrained their theoretical models.
Precisely. It's a testament to how precisely Webb can measure things and how that data, even the lack of extreme brightness, directly informs our understanding.
So the net is tightening. We're really moving from this vast universe of unknowns about FRBs to a situation with specific suspects, specific scenarios being tested. What does all this mean for our broader understanding of FRBs? And what comes next in this captivating cosmic detective story?
Well, this brings us right to the profound significance of the RB float discovery. As Professor Ido Berger noted, and it's worth repeating, dozens of different ideas have been proposed to explain FRBs, but until now we haven't had the data to test most of them.
That really highlights the core challenge they faced for years.
It does. Without precise localization and direct observation of the host environment, theories just remained largely untestable, floating in the realm of speculation. This is precisely why the ability to isolate individual stars or small stellar clusters around an FRB, like they've done with RB float, represents such a huge gain, as he put it.
It transforms FRB research, doesn't it?
Fundamentally.
Before RB float and this kind of precision, FRBs were like that distant thunder. We could hear the rumble of immense energy. We knew something powerful was happening out there.
Mm-hmm.
But the storm cloud itself, the source of the lightning flash, remained largely invisible, out of reach. Astronomers had to rely on statistical inferences from many detections, looking for patterns.
Trying to build a profile from afar.
Exactly. Now, for the first time, we're actually seeing the potential scene of the crime, pinpointing the origin with incredible clarity. and immediately following up with Webb's infrared eye to examine the immediate stellar neighborhood.
It moves FRB research from being primarily theoretical, based on inference and speculation, to being driven by concrete, testable observational evidence. That is a massive fundamental leap forward in the scientific process itself.
So this specific data point, RBF float and NIR1, regardless of the final conclusion on NIR1's exact role, it's invaluable, isn't it?
Immensely valuable. It provides a real-world scenario, a test case, against which to check all those complex theoretical frameworks. By connecting a specific burst to a specific type of stellar environment, whether it turns out to be the binary system with mass transfer or the young stellar cluster hosting a magnetar, it helps astronomers refine their models of FRB progenitors.
It narrows down the possibilities to the whole population.
Exactly. It helps us figure out what kinds of stellar systems and what kinds of extreme astrophysical environments can actually host these events. So this isn't just about understanding RB float. It helps us understand the entire class of FRBs. It's a massive step forward, but
There's always a but in science.
there usually is. As with all great scientific discoveries, it also inevitably opens up new avenues for investigation and naturally leaves some lingering uncertainty. Science thrives on that uncertainty, really.
And that uncertainty, that open-endedness, it is a fundamental and, frankly, exciting part of the scientific process. Dr. Blanchard openly acknowledged this, didn't he? He said something like, whether or not the association with the star is real, we've learned a lot about the burst's origin.
Right. Even if NIR1 isn't directly involved, its presence and properties tell us something important about the environment.
And he added, if a double star system isn't the answer, our work hints that an isolated magnetar caused the FRB. That shows the team isn't locked into just one idea, right? They're maintaining that healthy scientific skepticism, even about their own exciting findings.
That's the hallmark of good science. Follow the evidence wherever it leads.
He also mentioned of another intriguing possibility for that infrared signal from NIR1, didn't he? Something about reflected light.
Yes, that's another layer. He suggested that the infrared light Webb detected might not be from NIR1 itself, but could simply be reflected light, an echo, if you will, caused by a powerful flare from the actual object that caused the radio burst, perhaps an unseen magnetar.
So like the magnetar flares and NIR1 nearby just reflects some of that light, making it temporarily brighter in the infrared.
Exactly, like a cosmic mirror reflecting the flash. If that's the case, this reflected infrared light wouldn't be a steady emission from NIR1 itself. It would be expected to fade over time as the flare from the magnetar dissipates.
And that gives them a way to test it.
Precisely. This is a perfect example of how science pursues falsifiable hypotheses, constantly testing and refining. The idea of the infrared signal fading over time provides a crucial, direct observational test they can perform.
So what's the plan? Go back with Webb and look again.
That's exactly the plan. If they observe NIR1 again in, say, a year or two, and find that its infrared brightness has faded significantly,
then that would strongly support the reflected light from a flare theory.
It would. And that, in turn, would potentially strengthen the idea that an isolated magnetar nearby is the true source of the FRB.
But if they look again, and the infrared signal from NIR1 is stable, hasn't faded,
well, then the binary star theory, with NIR1 being a genuine companion star feeding an unseen neutron star, might gain significantly more traction. It would suggest NIR1's light is intrinsic, not just a reflection.
So the team will undoubtedly propose more Webb observations to search for precisely this kind of change. It's like a detective going back to the crime scene, looking for changes, gathering more evidence to corroborate or refute a hypothesis.
Exactly. More clues are always needed, and sometimes the absence of a change is just as informative as its presence. This dynamic approach, this continuous cycle of observation, hypothesis, testing, reevaluation, it underscores a fundamental truth about unraveling cosmic mysteries. It's an ongoing, iterative process, never really finished.
This systematic iterative process, constantly building on new data, it really brings us to the exciting future of FRB research, especially with Webb now in the picture. Professor Berger seemed quite optimistic about this new era.
He did. He stated, "We have taken the first step on a new path to solving the mystery of FRBs using the sharp imaging of Webb to zoom in on the precise locations from which FRBs are emanating." He sees this as more than just one discovery. It's a new methodology.
A new path forward. But he also noted the significant challenge inherent in this field, didn't he? The unpredictability.
Yes, that's the tricky part. He said, we can't predict when and where the next FRB will come from, so we have to be ready to quickly deploy Webb when the time comes.
That new path he mentioned really highlights the combined multi-wavelength power we've been talking about.
Absolutely. The precise radio localization from instruments like the CHIME Outriggers, they provide the initial alert. They pinpoint the location. That's step one.
And then step two is Webb zooming in.
Exactly. Webb, with its unparalleled infrared capabilities, can then zoom in with incredible detail on that precise spot. It offers a truly comprehensive multi-messenger approach. That synergy is critical for getting a complete picture of these extreme events.
But the unpredictability of FRBs, as Professor Berger mentioned, that sounds like a huge logistical challenge.
Oh, it is. How do you prepare for an event you can't predict, especially when valuable telescope time on instruments like Webb is so fiercely competed for, planned months or years in advance?
Right, you can't just call up Webb operations and say, hey, point over here right now. Can you?
Not quite. It requires incredible international collaboration between different observatories and teams. It means establishing rapid response protocols, setting up pre-approved target of opportunity programs.
Target of opportunity, meaning they have observing time set aside just in case something interesting pops up.
Essentially, yes. Programs designed specifically to ensure that when one of these fleeting bursts is detected and localized quickly enough by something like CHIME, precious telescope time on instruments like Webb can be deployed swiftly and effectively, overriding the normal schedule if necessary.
That sounds like it requires a huge amount of trust and coordination across the global astronomical community.
It absolutely does. It's a testament to the dedication and collaborative spirit of researchers worldwide.
It's truly the thrill of astronomical discovery, isn't it? Being ready for the unexpected, having the cutting-edge tools like CHIME and Webb, and the global teamwork in place to chase those cosmic flashes down the very moment they appear. It's an incredible era to be doing this kind of science.
It really, really is. The pace of discovery is accelerating rapidly now.
So let's try and wrap this up. What have we unpacked in this deep dive into RB Float, the radio brightest flash of all time? We've journeyed from the initial, really elusive discovery of these millisecond cosmic flashes,
Those ghosts in the data,
to pinpointing one of the brightest ever detected in a galaxy, NGC 4141, a staggering 130 million light years away. And then, thanks to this incredible synergy between ground-based radio telescopes like Shiki-Baccaris and the space-based James Webb Space Telescope,
that powerful combination.
we've even found a potential stellar partner in IR-1, or at least a specific stellar environment right at its origin. And we now have two incredibly strong, scientifically plausible, and most importantly, testable contenders for RB Float's genesis.
Right. Either that hidden neutron star in a binary system, ripping material from its visible companion star,
The mass transfer model.
or the isolated magnetar, probably young, residing within that nearby cluster of young, massive stars born from a recent supernova in that cluster.
The isolated magnetar model.
And the next round of observations might just tell us which path is more likely.
What truly stands out here, fundamentally it seems, is the sheer power and maybe even the necessity of combining different observational tools, specifically radio and infrared in this case, to begin to untangle one of the universe's most confounding puzzles.
Absolutely. We've moved from broad speculation and theoretical models that were frankly largely untestable
Just ideas on paper?
to concrete candidates supported by direct observation. We're making real, tangible progress on understanding what powers these incredible high-energy bursts. This multi-wavelength, multi-messenger approach is absolutely redefining what's possible in astrophysics. It's allowing us to ask and begin to answer questions that were previously just completely beyond our reach.
And you know, this isn't just about distant stars and exotic physics just for a handful of scientists, is it? It feels bigger than that. It's about pushing the absolute boundaries of our cosmic understanding, asking the biggest questions about the universe itself.
It connects to fundamental physics.
Yeah. It's about how every new piece of information, every faint infrared glimmer that Webb captures, every precisely localized radio burst from CHIME, brings us closer to understanding the fundamental physics of the universe, how stars live and die in these extreme violent ways, how galaxies evolve over cosmic time, and perhaps even revealing the kinds of extreme processes that shape the cosmos we inhabit, the universe that ultimately allowed for life here.
Well said. It puts our own existence in a much grander context.
So that leaves us with maybe a final provocative thought, something for you, our listeners, to mull over.
Always good to end with a question.
If the universe can create such astonishingly powerful millisecond-long explosions from seemingly ordinary, or at least now potentially understandable stellar systems and environments, processes that we're only just beginning to grasp thanks to tools like Webb and CHIME.
Right.
What other short-lived high-energy phenomena might be out there, yet to be discovered? What other extreme physics are waiting just beyond the reach of our current instruments, ready to challenge our fundamental understanding of the cosmos all over again?
It makes you wonder what else is flickering just beyond our view, doesn't it? What other secrets the universe holds.
Something truly profound to ponder the next time you look up at the night sky. Until our next deep dive, keep asking those big questions.